Morning. We have a lot to do today. So the first thing I want to do is recall what we did last time. Okay. Somebody tell me what the flow value is. Flow value. Oh, yeah. What's the flow value? How do we define that? The value of a flow. Yeah. Yes, it's the net flow out of the source. Okay? And we denote it by absolute bars around the F, and it is F of S comma V. Okay, so remember our implicit summation notation. Whenever we use a set, we mean the sum over the elements of the set. Okay? What's a cut? Who remembers what a cut is? I'm going to start picking on people. You're going to regret you came to class today. What's a cut? Now, we had flow networks, we had cuts of flow networks. Yeah. Good. Okay, any partition ST of V such that S is in S and T is in T. S being the source and T being the sink. And then we proved an important lemma last time that said the value of a flow was equal to not just the value of the source to everything, but also the net flow across any cut, for any cut. And the intuition for that was that, well, the source is in here, and the sink is in here, and everywhere else we have flow conservation, so there's no place for the flow to go except across the cut. Okay? And so, remember we did a proof that proved this that was basically a lot of manipulations of zero. Okay? Because everything always was summing to zero that you had. Okay, and for a corollary for that, okay, we proved that the value of a flow was less than or equal to the capacity of any cut. Okay, because each of the individual terms, that's the capacity constraint, that the flow not be greater than the capacity. Okay, we defined a residual graph. Okay, and this was the graph G sub S V E sub F, okay, with strictly positive residual capacities okay, C sub S of UV equal to C of UV minus F of UV. Okay, and we insist they be strictly positive. This is, by the way, a case mostly in this class, whether it's something has been strictly, less than or equal hasn't mattered very much when we're talking about asymptotics. But in flow, it's really critical whether you mean less than or equal. Okay, so this is the strictly positive, because something, if it's equal to zero, okay, that's the biggest it can be. Then it doesn't, that edge doesn't admit any more flow. If it's greater than 0, then it does admit more flow, and that's what we're concerned about, is whether we've saturated the edge or not. Okay. Can somebody remind me what an augmenting path is? Yeah. So it's a path, and tell me about the path.
It contains what more could be passed to the same path from one end to the other.
Sort of. Yeah.
The path where all the residual passes the residual separate themselves.
Yeah. Sort of. Almost. That's half, right? Okay. It's a path from S to T in the residual graph, which is the second part of it is what you said is for where the residuals are all positive. So it's any path from S to T in G sub F. Okay, and what's interesting about an augmenting path? Why do we care about augmenting paths? Yeah. Yeah, if you have an augmenting path, you can increase the flow value by pushing flow through that path. Okay, and the amount of flow you can put through the path is the residual capacity of the path. Which depends upon what the bottleneck edge is on the path. Okay, so the amount of flow that I can push through that path is the minimum along the path of the residual capacity of any edge. And that amount of flow is what I can shove through the path. Okay? And the reason that we can do an augmenting path is because any internal vertex is going to continue to satisfy the conservation constraint. Because since the path goes through the vertex, any flow that goes in will go out. And so the property of the residual of the flow conservation will be preserved in the path. Okay, any questions about any of these concepts? Everybody, just refresh people a little bit about where we were last time. Okay, because now we're going to get in, today we're going to get into a really important theorem and then into flow algorithms themselves. Okay, so we want to prove the following theorem. The max flow min cut theorem. And it's probably the most celebrated of the network flow theorems because it's the simplest and one of the very first. And it says that the following statements are equivalent. Okay? It says that the value of the flow is equal to the capacity of a cut for some cut. Okay? And that's the same as if F is a maximum flow. And that's the same as if F admits no augmenting paths. All those are equivalent statements. Okay? And the reason it's called max flow min cut, well, the max flow comes from this, and the min cut comes from this statement, okay, which says that if the value of the flow is equal to the capacity of a cut, well, we showed before that the value of a flow must be less than or equal to the capacity of the cut. So this must be the minimum cut in the graph, because if there were a smaller one, then the flow would have to be smaller. Okay, so that's where we get the terminology max flow min cut. Okay, so let's prove this. We'll start by showing that statement 1 implies statement 2. Okay, can somebody give me a one-line proof of this fact? Okay, if we have the value of a flow that's equal to the capacity of some cut, then argue to me that it's a maximum flow. Yeah.
Cannot be greater than the capacity of the like so we have the corollary of that.
Right.
Must be maximum.
Right. So it can't be less. Okay, if it's equal to the capacity, there's nothing that's going to be greater. Okay, that's all there is to it. Okay. Since the value of the flow is less, we're going to see capacity to cut by the corollary there. Then, if it's equal, it must be maximal. Good. Okay. Now 2 implies 3. So what we're going to do this is, I'm going to do 1 implies 2, 2 implies 3, and then 3 implies 1. And that'll show that they're all equivalent. Okay. So 2 implies 3. Somebody give me a one-line argument for that. Yeah. Yeah, if it had an augmenting path, I can always increase the value of the flow by the residual capacity of the path. And so therefore it would be greater, contradicting the maximality. Okay? So pretty straightforward. Okay? If there exists an augmenting path, flow could be increased contradicting the maximality of F. Okay, now 3 implies 1. Anybody see a one-line proof for that? If you do, you're pretty clever, because my proof has a lot more than one line. Okay? Okay. So we're going to try to show that if F admits no augmenting paths, then the value of the flow is equal to the capacity of some cut. Okay? So let's suppose that F admits no augmenting paths. So then let's define the following set. Okay, and we're going to let so we're going to say, let's take a look at all the vertices that we can reach along a path in G sub f. Okay, and we'll let that be S, okay, that we can reach from S. Let that be S, and everything else we'll let be T. Okay, so the basic idea here is that if there's no augmenting path from S to T, then, well, clearly S is in here, then T must be, the sink, T, little t, must be in here. Okay, because why? What if T were in here? Yeah. Yeah, we'd have a path in the residual graph. That would be an augmenting path. Okay, so T must be over here. Okay, so let's note that S is in S and T is in T. Okay, which implies that ST is a cut. Okay, and what we're going to show is that that's the cut for which is equal to that the flow value is equal to the capacity of this cut. Okay, so let's see how we do that. So let's consider a vertex U that's in S and another vertex V that's in T. So to draw a picture, here I have the source, here's U, and we're going to see that there's some path from S to U because that's how we know that it's in S. Okay, and then I can sort of conceptually draw a line. There's no reason that these would necessarily have to be contiguous. And then we have some V over here. Okay? And what I'm going to do is look at what is the residual capacity from U to V. So what is the residual capacity from U to V? Somebody said it? Yeah, if there were an edge here with positive residual capacity, then V would be an S. So therefore the residual capacity here must be 0. Okay, so if we look at this, we must have, which means it's actually not in the graph, okay? Okay, we must have C sub f of uv equal to 0. Okay? Since if it were bigger than 0, that would imply that v is in S. Good. Okay, so we know that the residual capacity is 0. So therefore, what is the flow value from U to V compared to the capacity of U to V? Well, let's take a look at what it means for the residual capacity to be 0. Okay, so this is the residual capacity. Okay, and if it's equal to 0, okay, it's equal to 0 since it's not in G sub f, then it says that C of uv is equal to f of uv. Okay, so therefore, f of uv is equal to C of uv, since C sub f of uv is just equal to C of uv minus f of uv. Okay? And now all we do is we sum over all u and s. Since u and v were picked arbitrarily from their respective sets, this is true for all u and s and all v in t. And so what we do is just sum over all u and s and v and t, which implies that f of st is equal to c of st. Okay? And since the value of the flow is just equal to f of st, we're done. Okay, we're done. So any questions about that proof? I mean, the clever part of the proof is defining the set S. Okay? That's the clever part, because that's where you say, okay, well, what cut am I going to use? And the answer is, well, let me look at every place I can get to. I can shove flow into everywhere, and now the question is, where am I blocked? Okay? And wherever I'm blocked, that's going to define a cut. That's the point. Okay? And that cut, you must have saturated every edge across that cut, because otherwise you would be able to push more flow to the other side of the cut. Okay? So that tells us the maximum flow. So this suggests a really simple algorithm for computing a maximum flow. Okay, a really simple algorithm. Okay, and that is, let me find an augmenting path and augment it. Let me find another augmenting path and augment it. And keep going until there's no path from S to T in the residual graph. Every time I augment it, I'll update the residual flow. And that's called the Ford-Fulkerson max flow algorithm. So let me leave some of those definitions up because they'll be useful. Okay. And Ford and Fulkerson are the most famous names in network flow because they were the people who started the study of network flow algorithms in a series of great papers, I believe in the 1950s. So their algorithm is pretty simple. Start by setting all flows to 0 on every edge. And then while there exists an augmenting path P, that's it. Just keep finding augmenting paths and augment them. Okay? And eventually, the argument is that you get to a maximum flow. Now, it turns out that if you have real numbers for capacities, this algorithm might never terminate. You can have a sequence of updates where every time you update it, you do update it, but the amount you're updating it by gets smaller and smaller. And you never actually, in finite time, get to the maximum flow. Even with integers, it can be slow. So let me give you an example of why it can be slow. Okay, so here's a graph. Do it over here. Okay, so here's our graph G. And capacities are these. Now I used to pick, these are all 10 to the 9th, a billion. Okay, I used to pick 10 to the 6th, but these days, 10 to the 6th, who cares? Okay, we're into the 10 to the 9th these days, so do billions, not millions. Millions doesn't impress anybody. Okay, so the algorithm starts out by setting all of these flows to 0. And then it finds an augmenting path. Now the residual graph is just G to begin with, okay, because if I subtract 0 from all of the capacities, I get the capacity. So I find a path. Now there are actually two paths I could take here. I could either go this one, okay, in fact if I took this one, then that would be good. So I'm not going to take that one. Okay, my algorithm, for better or for worse, finds this path. Okay, and so what's the residual what is the residual capacity of this path? Going here, here, and here. So remember, residual capacity, just take this minus that, so it's very easy. The residual, how much more flow can I push along that path? Yeah, 1, because this is my bottleneck edge, right? I can only push 1 unit, okay? So therefore, I push that unit, and I make this be 1, make that be 1, make that be 1. Okay? Now, I find another path. And this time, for better or for worse, my algorithm finds this path. Okay, now, I'm going backwards across this edge because I'm representing this. Remember, we're going to represent our flow networks with positive flow, okay, generally. But but we have to remember that we're computing things in the residual graph, and we always have to think about net flow. Okay, so a couple levels of indirection that you have to keep straight in your head. So so in the residual graph, there's an edge from here to here with what capacity? What's the residual capacity from here to here? Okay, it's just the capacity minus the flow. Come on, wake up. Okay, capacity is this, the flow is this. What's the residual capacity? I'm asking somebody to subtract. Very good. 10 to the 9th minus 1. Okay, and what's the residual capacity here? 10 to the 9th. Good. And what's the residual capacity from here to here? 0. Okay? But in fact, what's the residual capacity from here to here? 1. I can push 1 more unit of flow this direction. Why? I just don't ship the unit of flow that I'm already shipping. So therefore, this is an augmenting path in the residual graph, because the residual graph has no edge in this direction and has an edge of capacity 1 in that direction. Okay, so we push a unit of flow like this, and we update our flow values. That becomes 1. This goes back to 0. Okay, and this becomes 1. Okay, and so now in my graph, I'm back in the situation where I have 0 units of flow going from here to here, okay, and no flow going from here to here, because I just canceled the flow. So the important thing about flow is it cancels, okay, and that if I don't ship something, that's the same as if I stop shipping something I'm shipping, that's like pushing flow the other direction. So after 2 iterations, okay, I now have residual capacities here of 10 to the 9th minus 1 everywhere here. And I'm in the same situation I was here again. Okay, so I do the same thing again. I push the flow like this. And then I push the flow like this on the next one. Okay, because my algorithm is stupid. Okay? So how many iterations is it going to take for this to actually saturate and get what I ought to have been able to get with just 2 augmenting paths? How long is it going to take me to hit max flow at this rate? Yeah. Yeah, 2 billion. Okay, 2 billion augmentations. Okay, 2 billion augmentations, when in fact I could have done it in 2. If I pushed along this to begin with, the whole capacity here would have been 10 to the 9th. And then I would be able to push along here, and I would have found my maximum flow, which is in fact 2 billion. Okay? So historically, what's interesting is this was the algorithm everybody used, but when people looked at its performance, it was reasonably fast. Okay? Because it wouldn't do this. And this is when 2 very famous people came along. They weren't famous at the time, but this sort of made them. Actually, Edmonds was famous at that point, but Karp wasn't famous. Now Karp is famous. Okay. Okay, this is actually not their algorithm, it's their analysis. Okay, but we give it the name because they were the ones who noticed this. In fact, also there was somebody else a man by the name of Dinic, D-I-N-I-C, I don't know if that's how you pronounce it, in the Soviet Union, who independently discovered good algorithms for network flow. And but of course, since he was in the Soviet Union and we're in the United States, it's the same old story about whose name gets associated with the work, right? Like whoever people named it. So this was sort of ended up being named for Edmonds and Karp, even though Dinic did the work independently. So what they noticed is, so if I said I want you in a graph to find an augmenting path, that's just any path. What algorithms could we use to find a path from S to T in the residual graph? Suppose I'm trying to find a path from S to T. Any path. What algorithms do we know that will find a path from one vertex to another? Breadth first search. Any others? Depth first search. Okay, they're both good algorithms, and they're both good because they run in linear time, linear in the number of edges. Okay, so it turned out that most people who implemented this used breadth first search. And what would happen in this graph if you use breadth first search to find the path from S to T? Oh, I forgot to mention S and T here. Yeah. Yeah, it finds the good path. That's breadth first. And then the next one it'll find is this one. Okay? So that actually works out pretty well. So they examined the algorithm that augments along a breadth first augmenting path, which is to say just the shortest path where each edge in G sub F has weight 1. Okay, that's what we mean by breadth first pass. Remember, breadth first search is just a simplification of Dijkstra's algorithm, where you don't have to do a whole priority queue. You can get by with what data structure? Instead of a priority queue, what do you use for the data structure in in doing a breadth first search. Yeah, a FIFO queue, first in, first out queue. You put vertices that you're newly exploring on one end, and you always explore the ones on the other end. Okay, it's a tube. Okay, and finding an augmenting path is order E time. So that's fairly straightforward. And the question in the analysis of Edmonds and Karp was to examine how many flow augmentations do you need to do if you do breadth first search. Okay, and this is actually a fairly involved analysis, and it illustrates just a whole bunch of things that we've seen in the graph theory portion of this course. I'm going to drag you all through it. Okay, kicking and screaming, or mostly I've observed at this hour of the morning, people don't kick and scream, they just sort of fade out. Okay, and there are two major parts to the proof. The first one is a monotonicity lemma. So let me just see whether I can feel comfortable with throwing this stuff away. I do. In fact, one of the things I always think is amazing in the proof of this lemma is we have all these definitions and everything with flows, right? And we're doing network flow. I was just looking through, and the symbol F appears just sort of very discreetly in this algorithm. Okay, mostly what we're looking at is shortest path. Okay, so it's actually kind of interesting that you go, and in some sense confusing, because for all that we've done on cuts and so forth and so on, the max flow min cut theorem is going to allow us to to completely change the form of the argument. Okay, so we begin with a monotonicity lemma. Okay, so let's let delta of V be the breadth first distance from S to V in G sub F at any point during the algorithm. So at any point during the algorithm, we have some flow on the network, and we're working on some residual graph. We're going to find an augmenting path in that residual graph. Okay? And so the lemma says during the Edmonds-Karp variation of the Ford-Fulkerson algorithm, delta V increases monotonically. Okay, in other words, never goes down. Just keeps going up during the execution of the algorithm. Okay, even though F will change, we'll keep pushing more and more flow, but as I look at the distances, everybody's distance is going to keep rising, okay, during the execution of the algorithm. Even though every time we augment the flow, the graph is changing around from underneath us. Okay? Here's the proof. So suppose that F is the flow that we're looking at this point, and the augmentation along the breadth first path produces some F prime. Okay? So let's let delta prime of V be the flow in the shortest path distances in the residual graph G sub f prime. Okay, so we augment the flow. We have a new flow. We look at that residual graph. We look at those shortest path distances. So my goal is to prove this theorem. What's my goal? Given these definitions, what is it sufficient for me to prove? Okay, I want to prove that these things never go down. So what do I want to prove? Where am I headed with this? I'll start it out. For all v, basically, for all v, delta of v, I'll say it the opposite direction, delta v is less than or equal to delta prime of v. Okay, that says it's going up. Or it's not going down. It's really what monotonically increasing means. Okay? So that's what we're going to show. Delta prime of v is greater than or equal to delta v. Okay, and we're going to do that by induction on delta of v. The base case is delta prime of s, which is equal to delta prime, is equal to delta of s, which is equal to 0. The distance from the source in terms of number of edges from the source is always 0. Okay, so it's certainly true for things of distance 0. Okay, so now let's do the inductive case. So let's consider Brett's first path, S, that goes to U and then to V, okay, in G sub F prime. In fact, a lot of the action is going to be in the primes versus the unprimes. Okay, so this is the residual graph after we've done the augmentation. Okay, and let's take a look at what the shortest path values are along that path. Okay, so I claim we must have that delta prime of v is equal to delta prime of u plus 1. Why is that? Why is the shortest path from S to V in the residual graph equal to the shortest path to U plus 1? People did not do as well on the shortest path things on the quiz as I had hoped they would. Why is that true? Yeah. Right. Going through you, good. Right, so this is because subpaths of shortest paths are shortest paths. Remember that statement? Subpaths of shortest paths are shortest paths. This is the shortest path. Okay, in the graph where every edge has weight 1. Okay? So this is one edge, and this is the shortest path from S to U, because if there were one that were shorter, there'd be a shorter path from S to V. Okay? So that's certainly true. And it's pretty clear that UV is in E sub F prime. Okay? Because otherwise we wouldn't have that edge. Okay? So we're going to do two cases depending on whether UV is in E sub F or not. So it's possible that UV is in E sub F. It's possible that UV is not in E sub F, and we're going to handle those two cases differently. So it is in E sub F prime, that we know. The question is, was it there before? So let's take a look. Let's take a case where it is first. Okay. So then I claim that in G sub F, so that's when I do delta, it's in G sub F. This is the residual graph before I've done the flow augmentation, that G sub V is less than or equal to delta of U plus 1. So why is that? Excuse me? Triangle inequality. Good. You're ready for the final. That's the triangle inequality. The shortest path to V is shorter than the shortest path to U following the edge UV. Okay, just the triangle inequality. And that's less than or equal to delta prime of U plus 1. Why is that? Yeah. Yeah, induction. Okay, this is our inductive step because we're looking at doing induction on delta V, okay, and delta U's value is smaller. Okay, so this is induction. Okay, and that's equal to delta prime of V by what we just showed here. Okay, since this is a breadth first path. Okay, subpaths are shortest paths are shortest paths. So we're done with this case. Proved what we needed to prove. Okay, so if the edge is there, no sweat. Now the tricky case. The case when UV is not in E sub F. So we can sort of imagine, so we have G sub F prime, which is the after situation, after we've done the augmentation, and we have U connected to V. And G sub F, which is what we have before the augmentation, has U and V, okay, with no edge. Okay, how's that possible? How could I have, after the augmentation, have an edge from U to V, but before it, I had no edge from U to V? Yeah. Yeah. Which happened because okay. So there must have been an edge from V to U before. And what we did was, so there was an edge from V to U, and what happened when we augmented the the flow. We didn't necessarily saturate it, but we did push flow along it. And that created the edge from U to V. Okay, so we must have had this situation. Not only that, but the augmenting path that we used went from V to U. And that created the edge from U to V. Okay, everybody follow that? Okay, I mean, this is a clever argument. Okay, must have had that happen. Okay, so the augmenting path P must have du in P. And also, P is a breadth first path in G sub F. So we have, if I just can sketch it, for G sub F, we have our path P, which starts out at S. It goes at some point, it hits V. Okay? Then it hits U, and then goes on to T. Hits these in the reverse order, and we augment along that path. And that creates our edge from U to V. Okay? So now we just do a little math like we did before. Okay? Because we've now been able to figure out what the situation is, and we can do some math. And the math shows us that delta of V is equal to, I claim, delta of U minus 1. And why is that? Yeah. Yeah. It's plus 1 the other way because this is the shortest path. Okay, so it's a breadth first path. Okay? So subpaths of shortest paths are shortest paths. And that's less than or equal to delta prime of U minus 1. And why is that? Induction. Good. Induction. And that's less than or equal to delta prime of V minus 2. Ooh. Where'd that come from? Yeah, this one up here. Okay? Right here. Okay, because now we have the shortest path, the breadth first path in G sub F prime. And that's less than or equal to, it's actually less than, delta prime of V. And why is that? Right? Laws of math. Okay. Peano's postulates. Okay. So we've proved it in both cases. Okay, that it always that these values are always increasing as we go along. Okay, that's pretty cool. Okay. Okay. Now we're going to use that in the following theorem, which is the theorem that Edmonds-Karp proved. To show that we have only order VE flow augmentations during the Edmonds-Karp algorithm. That's an upper bound. Okay. So now we're actually going to get a number. Okay, so let's suppose that P is an augmenting path. Path that UV is some element of P, and it's some edge along P for which the residual capacity of that edge is equal to the residual capacity of the path. So this is the bottleneck edge on the path. Okay, if this situation happens, we're going to say that the edge UV is critical. Okay, on the path. If when we have the path, the bottleneck edge, any bottleneck edge, there might be more than one, is critical. What happens when I augment the path? What's going to happen in the residual graph to the edge UV? When I augment along the path? Disappears. Whew. Harry Potter. Whew. Okay. Right? Disappears. Okay? So let me do an example. So here's the residual graph. And it's got 5, 2, 3. Okay, oh, and we got edges going back this way too. 2 and 3. Here's a residual graph at some point, and I find an augmenting path which goes from S to T. What's the residual capacity of that path? Two. Okay? Which edge is critical? This edge, the one between the two unnamed vertices. Okay? The residual capacity of a path is the minimum of any of the capacities on the path, because that's what's going to limit how much flow we can push through. Okay? We can push 2 units of flow through this path. What happens when I do that? What is this? What happens to this graph? What happens to here, between these two vertices? So the residual capacity is going to go here, from here to here, down to 0. Okay? And so that edge is going to disappear from the residual graph, because the residual graph only has edges with positive residual capacity. What happens to this edge? Yeah, it increases to 5. Because now I can push back those 2, plus I can ship another 3 this direction. Okay? What happens over here after I ship 2 units of flow? This drops to 3, and I get an edge going back this way with capacity 2. Okay? And here what happens? Okay, this drops to 1, and going back this way I get 4. So the edge that's critical is this edge, because it disappears. And if I had several edges that had capacity 2, they would all disappear. Okay, they'd all be critical on that step. Okay, so here, C sub F of P is equal to 2. Okay, so let's see what happens as I So the first time in the algorithm that uv is critical, we have delta of v is equal to delta of u plus 1. Okay, why is that? So the first time we have along that the edge is critical, I claim that the shortest path to v is just equal to the shortest path to u plus 1. Why is that? What's going on there? I see we have some people who faded out. It's funny when I drag people kicking and screaming. Why is this? Yeah. Yeah, because P, the path that I'm augmenting along, is a breadth first path. Exactly right. Okay, and because it's a breadth first path, it's the shortest path and has the shortest path property. Okay, good. Since P is a breadth first path. Good. Okay. Now, I want to look for the next time that UV is critical. What has to happen before it can be critical again? Can it be critical on the very next augmentation? No, why not? Because it doesn't exist, right? It got removed. So what has to happen between now and the next time that it's critical? Yeah. It has to happen that we push flow from V to U. V to U doesn't have to be critical necessarily, but we have to push flow from V to U, okay, before we can push it back the other direction. We have to recreate UV, because UV has disappeared. It's going to stay disappeared until we push some flow back from V to U, okay? So we must wait until VU is on a new augmenting path before UV can be critical again. Okay? So let's let delta prime be the distance function when VU is on the augmenting path. So we're going to wait for that situation to happen where we're pushing in the opposite direction, and at that point we're going to stop and we're going to look at what's happened. Okay? And so at that point we have that delta prime of U is going to be delta prime of V plus 1. And why is that? So wait till we push the other direction, and that's because it breadth's first path. Okay? And that's going to be greater than or equal to delta of V plus 1. Why is that? Monotonicity. That's what we just showed in the previous lemma. Okay? And that's equal to delta of U plus 2. Okay, why is that? This one. Okay, once again, breadth first path. So what does that say? That says that between times that UV could be critical, the distance had to go up by 2. So the distance can't just sit there. Between critical values, it must rise. Okay? So let's just take a look at an example here before we go on with the proof. Here's S and T, and somewhere here we have U and V. Okay? And we have this augmenting path from U to V where this was critical, right? And therefore it disappeared. Bing, gone. But when it disappears, we know that there's a path that's created in the other direction. And when it disappears, we have, say, delta of U is equal, let's say it's 5 here, and this was delta of U equals 6. Okay? So we augmented and we got this residual graph, okay, or the graph where that's replaced. And now we have to have it the case that before it can be critical again in this direction, since it doesn't exist, we have to augment this way. And the point is that when I augment this way, okay, then that'll create this edge again. And now, at the point we augment this, this couldn't have gone down, so it must be at least 6 at this point. Okay, it might be bigger, but it's got to be at least 6, which means that now delta U here must be at least 7. Because if this is a Brett's first augmenting path, okay, so this has got to be at least 7. And so it went up by 2. Okay, from one iteration to the next. Yeah. Is this? That's a V. That's a V with a tail. Thank you. Okay. So the point is that for this event to happen, you can see it must go up by 2. And that's all the math here is saying. It's got to go up by 2. So let's see what that says. Okay. So the distances start out non-negative, right? Because all the edges in the graph have weight 1 to begin with. All the distances start out non-negative. They never decrease because of the monotonicity. Okay? And what's the biggest that they can get in a breadth first graph? Well, they can get up to infinity if they're completely cut off, right? That could happen. But before they hit infinity, what's the biggest they could be? How big could a shortest path distance, a breadth first distance in a graph be? Do you have any bounds on that? Yeah. Could be E. There's a tighter bound. That's true. There's a tighter bound. Okay, because you couldn't go over more than every edge. Yeah. V. Good. Okay, in fact, even a little bit tighter. V minus 1. Good. Okay, so they're less than or equal to V minus 1, okay, because in our breadth first path, that's a simple path, okay, no negative weight cycles, a simple path, until the vertex becomes unreachable, in which case it shoots up to infinity, and by the monotonicity lemma is never going to drop below infinity at that point. It's always cut off once it's completely cut off from the source. Okay? So how many times can UV be critical? Yeah. Yeah, something like v minus 1 over 2, because it goes up by 2 each time, and certainly order v times. Since delta mu increases by at least 2 between occurrences. Okay? Can only, because every time we get it critical, we've just shown it must have gone up by 2, by at least 2. So the number of times it can go up is at most order v. In fact, it's something like v minus 1 over 2. Okay? So everybody with me? Okay? So how many edges are there in the residual graph? How many are there to become critical? O of e. We showed last time it was at most 2 twice e. Okay? So they're order e edges in the residual graph. Okay? And every time we augment, some edge is critical. So therefore, there can be at most order VE augmentations. Because each edge can be critical at most V times, and they're E edges. VE, order E edges. Okay? So any questions about that proof? Really, I mean, quite remarkable that they, I think that they came up with this argument back when the study of algorithms was very, very early. Very, very early. Yeah. Oh, there are ones that use potential functions, even. Okay, there's great stuff here. There's great stuff. This is not the best bound. So let's just finish off the corollary. Let's get the running time, and I'll talk a little bit about what's been done since. The EK algorithm runs in O of V E squared time. Okay? And why is that? So we have order VE. Remember the algorithm. That algorithm was a pretty simple loop. We've just counted how many times we go through the loop. What goes on in each loop? Yeah, we find an augmenting path. How long does that take us? Okay. Takes how long? Order E. Okay. And we also have to update the residual, we have to update the flows. Okay. Now, in fact, the algorithms that you usually implement don't actually build the residual graph. They just go through the edges of the graph and just look to see whether there's any additional flow that can be pushed. Okay. There's no point in building a brand new graph. You just look at the edges and see if there's a residual capacity there, and if so, you count that as an edge in your breadth first search. Okay. So how much does the other bookkeeping? What does it take me to update the flow along an augmenting path? O of V. It's just a path. Okay? Per augmentation. Okay? Just go in and add a value to the flow value. That's all you're doing. Calculate what the minimum is on the path, and then add up what that flow value is. Not so hard. In fact, you actually keep the minimum as you're going. Okay? So, really pretty neat analysis. Okay? Use a lot of our understanding of network flows and so forth. Also, it turns out that, as you saw in recitation, this is an example of linear programming. Okay? That is not the algorithm, but the problem. Max flow problem is an instance of linear programming. Okay, let's talk about what's been done to date. Okay, so the best bound to date is by King, Rao, and Tarjan. Where have we heard Tarjan before? Yeah, I mean, actually, you hear, if you actually study algorithms, data structures, you hear Tarjan all the time. Okay, he's one of the, I think, one of my personal heroes. Okay, he's just unbelievably beautiful stuff that he's done. Okay, he's at Princeton, if anybody is looking at graduate school. Okay, Satish Rao, he was one of my students. In fact, I did recitations in 6002, where he was my student, and then later he was a UROP for me. Okay, great. So their bound is order V E log base E over V log V of V times. So this is almost as close as you can get to VE. I mean, this is really taking the log factor down when you take it to this base. Okay, not quite completely down. Okay, so that's the best algorithm. And Goldberg and Rao, again. Okay, so Goldberg was my PhD student. Okay, they have an algorithm, and look at this. This is amazing. Okay, so this is a different type of algorithm. This is one which uses the size of the capacity. So the Edmonds-Karp analysis, we haven't looked at the values of the capacity. They could be real numbers for all we care. Okay, and the algorithm would still do the right thing in that many augmentations. Okay, but in many cases we know that it's some integer in some bounded range. Okay, and so their algorithm works in this: min of v to the 2/3 e to the 1/2 times e log of v squared over e plus 2 times log of c, okay, where c is the maximum capacity of any edge. Okay, it's an integer. This is an integer problem. So if you just take a log of the maximum capacity, well, that's not too big, because that's typically the number of bits that you're using in your representation. So you're saying for each bit, it's going to take you something times this. And what is this? Well, there is this log value here, but notice that this is less than VE. It's either V to the 2/3 E times some logarithmic junk, okay, or it's at the most E to the 1/2. Okay, and since E to the 1/2 is smaller than, since E is smaller than V squared, E to the 1/2 is also smaller than V. So this is actually beats the VE bound, okay, by with all these other sorts of things. And in fact, if you're interested in network flow algorithms, Goldberg has a website with a whole bunch of really excellent codes for shortest paths and so forth, because he's both very interested in the theory and very strong in theory. He's also a very strong programmer and very interested in fast implementation. Okay, so very nice coupling of if you will, course 18 with course 6. Okay, so you can go to his website and see a bunch of things, see a bunch of good codes. So that completes our discussion of network flow, except for the discussion we'll have on the final. For the final, I want everybody to tell their friends that the room has been moved. It's announced on the web page. It will be on the first floor of Building 2. We're going to break you up into recitations so people have tables, rather than having you on little things in 10-250, which is a lousy place for rooms. So we got basically separate rooms on the floor of Building 2. Also, next time, invite your friends to come. We have a whole bunch of people who've entered the programming contest. Yep. And you know, we hope to make some awards there, and I'll tell you a little bit about what's coming up in algorithms, and it'll be our last lecture, and we'll have something special. Okay?